English? Who said? Lorraine? You did? Oh, you? Okay. Alright. You didn't know what you were copying. Yes, that's a problem. Alright, let's have a look at the next lesson. Sorry, did you write this down? No, okay. Ready? Yes? Kinetic model of gas. Okay. So you remember we did pressure in mechanics. Do you remember pressure? Yes? So pressure is force divided by area. If you remember that, you don't need to write it down. Pressure is force over area. Do you remember the units? Newton per meter squared. The units are pascals. We say 1 pascal is 1 Newton per meter squared. Okay, so I don't know if I gave you the definition. Did I give you the definition of pascal? Well, 1 pascal is 1 Newton per meter squared. So, can you write this? You don't need to write this if you remember it, but I would like you to write the next definition, please. Got this? 1 Newton per meter squared. So if you want, it's like this. 1 pascal is 1 Newton per meter squared. It's the same as 1 Newton per meter squared. Yep, continue. Right. So we shall consider our ideal gas to be as shown. Have you done with Lorraine ideal gas? Have you done gas? No. What are you doing now? Lab report. Okay. What was the last thing you did before lab report? Periodic table?
We did group 2 and group 7. Group 7.
Okay. So we have this thing called ideal gas. It just means a simple gas. So for a simple gas, we assume, number 1, it's low density. So let me just be very clear. You have gas. You know what a gas is. An ideal gas is like a simple picture of the gas, a simple understanding of the gas, a simple, not complicated. You know what I mean? No, you don't. So for example, here, look, if I was moving this across the table, what forces are on it? There's my hand, and then there's the force going backwards, yeah? But there's actually many forces, aren't there? Because there's the weight, there's the reaction, there's the air, maybe someone shakes the table. So by ideal, we mean simple picture, you know, just a couple of forces, just a couple of ideas. No? What's another word I can use for ideal? Yes, ideal also means the best, but not here. Sorry to tell you this. Okay, now the best. The best type of gas, the easiest to understand. That's what it means here. Easiest to understand. Yeah, a gas that's easy to understand.
Wow.
Yes. By easy to understand, I mean there's not many difficult things happening. Just simple movement. Yeah. So you need to write these down because in the exam they sometimes say what are the assumptions of an ideal gas. What are the things you think about for an ideal gas? So the first thing, if a gas is ideal, it should have a low density. Okay. So firstly, number one, a low density. So could the air in this room be an ideal gas? I think maybe so. The density is quite low. There's not much air. I know it feels like there's much air because you can breathe, but there's not much air in here. There's not much. So a low density of, number two, colliding particles. So, you know, colliding particles, like particles that go like this.
Wait, a low density of colliding particles?
Yeah. Yeah, and I'm given as one sentence, but I'm separating out the ideas by numbers. Do you understand colliding particles? You know, like crashing together? So the air, one here, and crashes. Collided, you know, from mechanics, like the two cars. Yeah? But the difference here is that they don't stick together. Instead, the air bounces. Yeah? Colliding particles, and there's no attraction between them. So the particles move whatever way they want. They don't care. They just move anyway. Yeah? With no attraction between them, and we ignore gravity. So we have balls. Small balls bouncing around in a box. That's what we have, with no gravity, basically. So this is what we picture when we picture the ideal gas. Lots of little balls moving around in a box. Something like this. So the air in this room is like lots of little balls, and they're bouncing, and they're bouncing, and they bounce into each other. Yeah? You seem so confused. You know atoms. So there's atoms moving around. That's the picture. The air is little atoms of air, bounce, maybe they bounce like this. They're just moving around all the time. No?
Does this happen in normal gas?
It happens in normal gases, except we have a simple picture here, because look, for example, I said no gravity. But of course there is gravity. So this is a simple picture, but yes, it happens in all gases, they move around. But of course it's too simple, because there's no gravity, and sometimes, you know, maybe they stick together when they hit. Yeah, like this will be like in space. There's no gravity.
In ideal gas,
Yes.
there's no other force.
Yes. Ideal gas, there are no other forces, no gravity, no anything. If you want, yes. Okay. We understand the idea maybe a little better? Yes. Okay. Did you write down the assumptions? Yeah? I think it'd be good if maybe you can put little numbers to help you. Oh, you did? Okay, thank you. Yeah. In the exam, they sometimes, not often, but they sometimes ask you to say what these assumptions are. Okay, now I think they would like, they would usually want all four of them. Oh, that's a beautiful box. Okay. You can draw it if you want. And we'll have to go to the next slide now. Continue? Yes? Anyway, yes. That last sentence is wrong. Let us see what formula we are producing for this model. Bad grammar. Let's see what formula we can produce for this model. Okay, can I go on? Yep. Okay. I'm going to try and do the proof. Please be patient if I forget. It's a long proof. Okay, so firstly, write it down, but wait until I write a couple of lines to make sure I'm happy with it, okay? Right. So I'll start off by drawing my box. So we'll say this box is L multiplied by L multiplied by L. So you have, let's look at one particle. It's moving around the box. Yes? So to make this picture easier, I'll just look at it like this. There's a wall, and there's the wall. And then how big is this? This is L. And the particle comes in, hits the wall, and then hits this wall, and it's going back and forth like this. Yep. Alright. So, let's give it a speed. We'll say the speed is u for the particle. So it's heading this way with u. Okay. So we are looking, here we are here, and we are looking at the wall here. So what do we see? We see a particle come along, hits the wall, and then changes and moves backwards. So let's look at the change in the momentum. Let's say its mass is m. Before the collision, it's mu, and then after the collision, it's minus mu. Why is it minus mu? It's heading to the left. Yeah. So the total change is 2 mu. Okay, I'll just give you a minute to write this bit down. You can draw the pictures if you like. His eye is looking.
But is it supposed to be minus mc?
Yeah, if you want, here, Harim.
Because the u is...
It's mv minus mu is the formula. What's this called? Do you remember?
Momentum.
No, this is called the impulse, the change in the momentum. What's what? The circle. So, yeah, you have the two walls, and it's going thump, 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 like this. Yeah. Of one little atom. Yes. Here, afterwards, it's minus mu momentum, because here it's u, but here it's minus u. It's going to the left, and here it's going to the right. And the minus here is from the formula, mv minus mu. That's the change in the momentum. The change. It's okay, continue or not?
Here is you.
Yes. Yes. Continue?
1 minute.
Here? Because I just called the speed the letter u. So before the collision, the v is u, and then after the collision, the u is minus u. It's maybe I should call it like u0 if you want, and this is u0. So before the collision, oh sorry, that's the wrong thing. u0 and u0. So before the collision, it's u0, and then after the collision, it's minus u0. Does that make it clearer? Yep. Okay. Right, continue. So what I'll do now is I'll divide both sides by the time. Now, if I use my distance, speed, time, because it's constant, what's the formula for the time? It's distance over speed, correct? And what's the distance? Well, what's the speed? What's the speed? U. And what's the distance?
L. Right?
No.
Half L.
No.
I don't know.
So the distance, it's the distance it travels between hitting the wall here. So it goes left, right, hit. Left, right, hit. Left, right, hit. And you're looking here. So the distance is actually 2L. So this is 2L. So this cancels this, and that comes up here to make it squared. Who remembers what this is? Also known as F. Yes? So this is mu squared over L. Now what's the formula for pressure? Force over area. Yes? So, if I divide both sides by the area, I get now pressure equals mu squared over.
Wait,
yep.
Why did you cancel the u up there?
No, I brought it up to the top to make it a square.
Oh, okay.
And here I divided both sides by A, so that I can change this into pressure. Now, what is A? If I go back to my picture, what's A? Oh, not cubed. The other word? L squared, yeah. That's the area. So, this is L squared. So pressure equals mu squared over L cubed. But what's L cubed? What's L cubed?
The volume.
Yeah, pressure equals mu squared over volume. Yes? Okay. Can I go to the side for the next part? And then I'll come back to this. So, if you look here, this has speed v, and in one dimension, its speed is v. Now, let's say this speed here is v. In two dimensions, you have a part here and a part here. Yes? Now, we don't know this angle here, but if it was about 45 degrees, how big should this one be? V cos 45 and V sin 45. Will it always be 45? No, of course not. It changes, but it's about V over root 2. Cos 45, sin 45. So, if you had 3 dimensions, and you can break this V up 3 ways, 1, 2, and 3, how big do you think this would be? If you had to guess. Not half? V over, well, I'll tell you. I don't expect you to know. It's V over square root 3. Now that's something that we'll do in maths in the second semester. I don't need you to know that, but I want you to try and get the idea, because it's like it's going V over square root 1, and then in 2 dimensions it's V over square root 2, and then when you have x, y, z, and it's moving here, you have 3 parts, x, y, and z. Each of these is about V over square root 3. Roughly. So, if this is u, then what would this be? Yeah, it'd be root 3 u, because you're going backwards. Here we went from v to v over root 3. So if this is u, then originally it was this. Yeah? Now, if I go back here, will the particle be moving this way? No, it'll be moving many ways. So this u is not really u. It should be m root 3u squared over v. And this here, this is in 1 dimension, but this here is in 3D. That's the difference from here to here. From here we're just going 1 dimension, but here it can move many different ways. Yeah? Wait, sorry. No, bad teacher. My mistake here. We need to say, no, it's still the same idea. We need to say that the speed is u. So if I go from 3 dimensions to 1 dimension, what's it here? U over root 3. Yes? So what I really should say here, I am so sorry, it's like you start again, but instead of having u, you replace it with u over root 3. So I have it the wrong way. It's not this one. it should be u over root 3 here. Okay, that's better. So this one here is u, but this one here is u, and here is u over root 3. Okay, so we get PV equal... Where? Back left? Yeah, this one here became u over root 3. Oh yeah, so what happened was, in my picture at the start, here, there's the wall, and there's the wall. So instead of this, I now have this. So it means this piece is u over root 3. So this speed here now can be an angle. So this part here is u over root 3. No, the speed is still u, but now it's u in 3 dimensions. Do you hear that? So the speed is still u, but u in 3 dimensions. So this piece here is u over square root 3. That's the change that you make for the next part. So PV is, if I take the V up here, 1/3 mu squared. Nearly. Almost. Just a little bit more. Because this is only for one particle. Yes? So, now we have n particles moving around. So the m, I need to multiply by n. So, sorry, multiply by n. So I get NPV equals 1/3 nm u squared. Okay, we're nearly there, I promise you. Oh, sorry, no. This here is only for one. But this here is the total. When you have n of them. So this here is only for one, but this is for the total. Okay, PV equals n over 3 times 2 times 1/2 mu squared. We're nearly there, I promise. Now, do you see what I did on the next line? I put in a 2 here and a 2 here. So is it the same as the last line? Yeah, the only difference is I put a 2 and a 2 here. But can anybody see why I would want the 2? Does 1/2 mu squared look familiar? It's kinetic energy. So, this is the kinetic energy of one particle, yes? So if I multiply it by n, it's the kinetic energy for all the particles. So PV equals 2/3 total kinetic energy. But energy equals kinetic energy plus potential energy. Do we have potential energy in this example? What's the formula for potential energy? mgh. But we don't, because remember I said at the start, no gravity. So then the energy will just equal Ke. So now you can get PV equals 2/3 the energy. And to finish, the energy equals 3/2 PV. E energy, yeah. Now it's a long proof, but it's important because if you think about it, in this room, the air is moving, isn't it? Yes? We're not ready. Ready? No, V is the volume. Yes. So in this room, the air is moving, true? So if I ask you for the total energy, you'll have to get the energy here, plus here, plus here, plus here. It's a big calculation. Yes? Wow, look who made it. Finish at GMID?
Yes.
Yes? You have to go back?
Go back.
The GMID? Or all finished?
All finished.
Oh, good. So as I was saying, if you want the total energy in this room, you would have to add the energy for each atom. That's difficult, right? Isn't it? But here, I could say the total energy in this room is 3/2 the pressure, the air pressure, multiplied by the volume. Is that an easy calculation? Yeah, it is. So what you've done is a calculation like all the energy in the air from the motion of the atoms. You can easily find it by using this formula, 3/2 PV. Okay. Now it only works for a gas, but it's pretty good for other things too, like a liquid. Yeah? You understand that there's many atoms in this room, and each one is moving, and each one has a kinetic energy. So the total energy is this one plus this one plus this one plus this one. That's a big calculation. Difficult calculation, but this is an easy calculation. So I know the pressure in this room is about 1,000 kilopascals. And can I know the volume? I can. It's, whatever, 5 by 4 by 3. So this proof is important. Will you need to prove this in the exam? No. But you are expected to, for the exam, explain the idea of this proof. So the idea of this proof is you consider the motion of one atom and how it hits the surface, and from this you try to get this formula. I mean, this question has never come up in the exam, but it's on the syllabus. It says students need to understand this proof, but it's never been on the exam, and I have 30 exams. So I don't think it will come up on the exam, and I don't expect you to remember the proof, but I do hope you at least understand the kind of idea for the proof. Yeah? Continue? It's only for gas. However, if you use it for liquid, it will be quite reasonable. It won't be perfect, but it'd be not too bad, But you're right, it should only be for gas. It doesn't work so well for liquid, and it definitely doesn't work for solids. Okay. Next. So what makes this result interesting is that, okay, so I kind of talked about that. Yes, now, it doesn't matter, I wrote the 3/2 on the right, but you can bring this up here and write it 2/3, it doesn't matter. So we already talked about this result, okay. Right. So you know, when you climb up a mountain, what happens to the air pressure? You know this? It decreases. So as you go up, you get less air. The air pressure decreases. And also, when you go underwater, what happens to the air pressure? The pressure? It increases the further down you go. So if here's the ground, when you go up, what happens to the pressure? It decreases, and then when you go down, it increases. So in other words, from here up to the sky, the pressure is going down, 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 down. So here is at the most, here is U, and then here is at the top where it's small. Yes? Now, on the ground, we call this pressure 1 atmosphere on the ground. And this is equal to 101.35 kilopascals. And I think my K should be a small k, not a big K, but it doesn't matter. Kilopascals. Do you think it's always 101.35?
No.
No. On sunny days, is this more or less on a sunny day? More. And on a cold day, it's less. Also, this is only at sea level. Sea level, ground level. The same level as the sea level. Some countries are below sea level, and some countries are above sea level. You know what I mean? Yeah? I don't know about China. What about Malaysia? It's at sea level?
I don't know, but I know Bangladesh is below sea level.
Bangladesh is below sea level. And what about Korea? At sea level? Above sea level? Below sea level? Below? The same level as the ocean, as the sea. So here's the sea and here's the town. So the town could be above the sea, at sea level, or below sea level. So right now, I think we are maybe 200 meters above sea level. I think so, about 200 meters above sea level. Griffith College is. But then when you travel to the city centre, what do you think happens? You'd be at sea level, a little higher maybe. Yeah. Some countries are below sea level, so they have to build a wall, otherwise problem. And some countries are above sea level. Yeah. In South Korea, what do you know? Don't know. Above, at, or below? Maybe above. Yeah, okay. Do you have mountains in South Korea?
Yes,
Many mountains. Okay, well then you're probably above sea level, I think, then. If it's mostly mountains, then. Yeah? Okay, so write this number down, you need to know it. Well, you don't need to know it, it's in the formula book. This is called 1 atmospheric pressure. 1 ATM. This is the pressure at sea level. From the air. Okay. It's pretty big. Right, so, another proof, but much easier than the last one, I promise. Okay. Let's have a look. Okay, so let's say here is the sea level, and then do I want to make it a ball or do I want to make it a disc? Maybe it doesn't matter. We'll try with a ball. No, I'll go with a disc. Make our lives easier. Okay. Right, so this here is radius is or. No, sorry. I'll go with a ball. Radius is or. Okay, so let's put it underwater a distance of h. So there's a force on it. So the pressure will equal the force divided by the area. Yes? True? Yes? Now,
is that the particle?
This is just a ball.
Oh, okay.
Think of it like a football. Something underwater. Okay, does anyone remember the area for a ball?
2 pi square.
No, ball, not circle.
4 over 3 pi.
No, that's the volume.
4 pi r.
I think it's 4 pi r squared. And then there's a force here. Yes?
4 pi r or 2 pi r?
No, I don't remember. It's something pi r squared. We'll just put a question mark for the moment. We'll check it in a minute. Okay, so what's the force? What's pushing on this ball?
C?
The ocean, the sea, yeah. All the water here is pushing on it, isn't it?
Yes.
So actually, you know what? A ball is difficult. Let's go with a circle. It's easier, okay? So rather than a ball, we'll make it a circle. And the water is pushing down on it. And again, it's still the same, height h and radius r. Alright, so pressure is force over area. What's the area here? Pi r squared. Okay, now the force, what's the force here? What's the force?
The mass of the...
It's the weight of the water that's pushing down on it, isn't it? So what's the formula for weight? mg for weight. Yes, the force is the weight of the water. Do we know G? We do. Do we know M? We don't. So I have density is mass over volume. So mass is density multiplied by volume. So I can put that in. And I get density volume G over pi r squared. What's the volume? What's the V? The volume. What's the volume? Pi r squared h. That's the volume of the water times G over pi r squared. Now, this is very nice. What cancels?
Pi and r.
The pi and the r squared. So you get this formula. The pressure is equal to density multiplied by G multiplied by h. And do you need to know how big the circle is? No, the size is not important. There's no or. What do you need to know? You only need to know the height and also the density of the water if it's in water. That's if it's in water. If it was in a gas, then it's the density of the gas. Yeah. Enough?
Yeah.
So, if I make the H bigger, what happens to the pressure? It gets bigger. So if I make the H bigger, the pressure will get bigger. So if here's the ocean, here's my fish here, pressure 2, pressure 1, which is bigger? Pressure 2. Because the H is bigger.
The H is minus or plus?
We take it as plus, yeah. So we'll take down as plus in this picture. Yes? Okay. Can I go back to the slides?
No.
I need you to have this.
What about the proofing thing?
You don't need to proof for the exam.
Oh, just put it in this.
It's nice if you understand it or even write it down. Do you want to do that?
Yeah.
Which, understand it or write it down?
Both.
Oh, great. Yes? Okay, continue.
One minute. Okay.
Yes? Okay. Right, so I want everybody to try this for me. What is the pressure if you're swimming 5 meters under the sea? It's water, which is, oh yes, you missed that class. 1,000.
But isn't this the salt water is 1,030, right?
Okay, use 1,030 if you want. I suppose I did say sea level. Right, what answer did you get now? So it'll be
4905.
about 49,000, maybe nearly 50,000, is it? 49 something, yeah. 49 kilopascals. Yeah, did you get that? Yeah. Okay. Next one.
Wait, how is it 49?
Huh?
So it's 1030 times.
Yeah, so the rest of us use 1,000 for the density.
Right.
Yeah.
Wait, so it's 49,000.
Kilo. 49,000 pascals, yeah? So 49 kilopascals. Okay, continue. Right.
So it's Pascal is CA, right?
Yes. Everybody's so tired.
Yeah. Okay, I'm very early.
Oh yeah, GNIB. What time?
I go to embassy.
Embassy?
Yeah. No job.
Oh, you went to the Chinese embassy?
Oh.
Oh, what time?
You mean get up or?
Yeah, what time did you get up at?
Maybe half past 7.
Oh, please.
It's for me, it's too early.
I thought you were going to say like 4 a.m. or
No.
something. 7:30.
Yeah. And I run, take one bus and change to another
Every
bus.
day I wake up at 6:45.
It's impossible for me to get up early.
Yeah, okay. 7:30 so early. Okay. What time did you wake up at?
She wake up early than me.
Earlier.
I wake up at 7 o'clock.
Good for you.
And because my arms problem, like
Sleep until 7:30? That's okay. That's okay. Who have you got at 9 o'clock? How late were you? 15?
But she is not in the classroom.
Oh, was anyone in the classroom?
Yes.
Oh, shocking.
Yeah.
So you were okay?
Yes.
Alright, good. Now for this one here, do you know this word atmosphere?
No.
No. Okay. So look, Earth, space, atmosphere, the air. You know, so like here you are on the ground, and then atmosphere, and then there's a limit, and then you have space, no atmosphere. So this, you know, is the atmosphere. And I want to know how big is this atmosphere? Okay, so what information do you know? So here's the atmosphere, and you want the height. That's what you want, okay? Do you know the pressure?
No.
I do. One atmosphere. 101.35.
It's water?
No, air.
That's the pressure.
That's the pressure. Yeah?
But what's the density?
Well,
That
that's,
is one, right?
it's a little more than one. You can take it as one, but we'll get to that in a second. So, do you know the pressure?
One.
Yes, it's 1 atmosphere. Yeah? Do you know the density of air? Well, maybe you remember it when we did the mechanics. We did the mechanics lesson. Remember about the air pushing the person? Does anyone remember roughly? You remember.
One.
The density of air is about 1 kilogram per meter cubed. So it's about 1. What's it for water? 1,000. Air, about 1. I think it's 1.4. So the density is 1.4. Do you know the G?
Yes.
G is 9.81. What else do you need to know? That's it? Yeah, that's everything. So, give me the H.
7.38.
What is the pressure?
7.38 watts.
Meters.
No, you know it's not meters because you would have a big problem if it was only 7 meters, right?
I mean,
You forgot the 1,000 in kilopascals.
Oh.
Rho is about 1.4 for air.
What is the pressure?
So this here, the pressure is 1 atmosphere. I gave you that a few minutes ago. The density is about 1.4. The G is 9.81, and the H is what I want. And by the way, this is kilo, so there's 10 to the 3 here.
Wait, so it is 7379 meters. Is it still wrong?
735 meters. That means if you like go Wicklow Mountain, you have no atmosphere. Come on, you know that's not right.
It's 101.35 kilo.
Times 10 to the 3, yeah?
So that's the answer.
Have we got a real answer? Now that's meters, so make it kilometers. Now that's meters, make it kilometers.
7.379 kilometers.
Yes. What's it there? It's a 7.38 or something. Yeah.
Always
For a number like this, yeah. So what that means is you should have air for about 7.38 kilometers. And then after this,
No air.
no air. Now in real life, it's not like this. In real life, what's happening is the air gets less. So after 7.38, you still have some air, but it gets less. So then maybe after about, I don't know, 20 km, there's no air. But for us humans, we should be okay for about 7 kilometers. But then after 7 kilometers, we'll need to take some air with us. So you know the people who climb the mountains? Sometimes you see them with the big air cylinders on their back. So they can breathe when they're at the top. Okay? So 7 kilometers is good. By the way, is the H from here, the ground to the top, or from the top to the ground? What's the H? I know it's the same, but do we measure it from the ground to the top, or the top to the ground?
Top to the ground.
Very good, the top to the ground, yes.
Why?
Because remember, it's like the air is like the ocean, and you measure how far down you are from the top, not how far from the bottom. Yeah. Okay, good. Right, homework. I think so. Did I skip a question? Yeah, no, that's it. Got this? Yes? Okie dokie.